Hello. Hey everyone. Um, Welcome back to the stream. My name's Samuel Bennett, and in this stream, we're kind of creating like a bit of a rendering engine in using Vulkan in Haskell. Um, I apologize, my stream schedule has been very inconsistent lately. I've had a lot of like stuff going on in my life, and I'm trying to find a job at the moment, that sort of thing. So I don't have a lot of rhythm in my life, but hopefully when I sort some of that stuff out, we can get back to a regular schedule. So, what happened last time? Last time we were working on this example, and particularly like we ran into an issue where when we resized the window, it would stop working. So, you see if I can reproduce that. So let's see. If I stashed it. Here we go. Restore Z pop. Yes. Okay, so the we tried to make the frame in flight um, mechanism thread safe and exception safe, and we tried to do that, and then we tried to demonstrate that that would work with a multi-threaded kind of runtime, and it didn't, and I was very confused. So let's see if we can see that issue again. So it's after we resize the window. Yeah, then try and close the window and nothing happens. And it kind of only works after we resize the window again. And oh gosh, it's very confusing. And look at, oh gosh. So yeah, the other thing is that if we resize the window once and then resize the window again, we just get this freeze. And then if we try and like close the window, then it works again, which is weird. And oh, and now I can't close it. And let's try and sort these windows out. If I try and cancel it from here, it only gets the cancel message when I resize the window. So yeah, weird stuff going on. Now, uh, when we resize the window, a swap chain out of date exception is thrown. And so I'm almost certain that it's got something to do with this function here with handling that swap chain out of date exception. Um, and the sort of thing that the hypothesis I've come up with is we're looping within the handler of that exception. So when we get that exception, we're retrying the computation in the handler, which I think is a bad idea. But honestly, I was trying to do some research and I couldn't find anything that said, "Hey, don't do that." Um, but what's happening is that it's kind of swallowing any asynchronous exceptions that happen in this block. So like everything's fine until we loop. So everything's fine until we get the first swap chain out of date exception. And then when we loop, all of a sudden any asynchronous exceptions we send are just like ignored, which is where that unresponsiveness comes from. Like we can't interrupt it, we can't quit it. Um, yeah. So what we can try and do instead, and we can see if this fixes the problem, is rather than doing like a catch and then handle thing, we can do a try. So we like try, we get a result, and then we do something based on that result. And that way, if we loop, we're not looping in the handler. And so hopefully that should fix the whole swallowing exceptions issue. So how might we do that? Well, the first thing we do is we're just going to try the user's function pass to them the initial swap chain. And then, in case that result is a swap chain out of date exception, then we can do this stuff. So we get the frame buffer size, create a new swap chain, free the initial swap chain, and then retry the computation. But in case this successfully returns, we just return that result. So a small change, but one I hope will fix the issue. Oh, okay, I'm using the wrong try, I think. Try. Yeah, let's use lifted try. Okay, that compiles. So only different is really that we're just not looping the computation or retrying the computation in the handler of the last exception handler. So let's see if that fixes it. Oh, yeah, it's looking good. Yeah, great. Okay, well that was enough to fix it, so that's nice. Um, cool, we can keep that. Just get rid of that. Alright, let's commit this. So fix retry on swap chain out of date. Such a big, big function name. So swallowing async exceptions. So retry was swallowing asynchronous exceptions. And I did do a little bit of investigation of this on off camera, so that's why I kind of jumped straight for the conclusion. To explain honestly. Cool, commit that. We can just have a look quickly at try versus the alternative catch. So with try, it's using catch under the hood, but we're always returning out of the exception handler. We're either returning with the result, or like we're either returning with a successful result or there was an exception. So always getting out of the catch blocks, the two functions that are passed to catch. Um, Whereas previously what was happening is that we were in the handler, so in this argument, looping again. And so I'm not really sure what happens here with this, IO catch hash. Like I'm not sure what's going on here, but it's a different, it's certainly a different, like execution context, um, like us looping in this handler here, because then we've got a nested catch in the handler and then another nested catch, depending how many times we resize the window, we're building up this list of like nested catches. Um, so yeah, maybe someone can tell me, why this is how it is. Um, but as for now, I have no idea. But I do know it doesn't work, so we won't use it. Let's see if we've got anything here. Yeah, nothing there that's telling me not to do it. Oh well. Okay, let's also commit making this example asynchronous. So we can actually it's kind of cool. Now that we've made this uh, exception safe and thread safe, we can like kind of run as many render threads as we like, um, and we won't have any issues, which is, a real power move, I think. Okay, yeah, so it's still working. Let's see if we can get some statistics. I don't think it'll make anything faster. Well, it almost certainly won't. Um, because like we're not doing much each frame, so it might actually make it slower to use multiple threads. Um, but let's have a look. Just trying to remember what the extension name is uh for a render doc. Render doc's a program that's used to kind of debug rendering rendering programs. So yeah, we can get some statistics about the time it takes to render each frame. These probably aren't going to be as accurate as other timings, like if we were to do it ourselves. But here we go. Looks like we kind of got some stuttering. But that could be because I'm recording as well. I didn't notice that before. See if we get rid of the stuttering if we don't do this concurrently. Uh, gosh, it's hard to tell. But it does look like that's stuttering less. Let's go for like 3 rendering threads and see if it gets worse. I wouldn't say it gets worse. Maybe. I don't know. We'll have to investigate that further later. But for now, this is cool. We've got a separate render thread and an event loop. Okay, so we will uh, multi-thread uniform example. Okay. So, another source of like kind of exception unsafety right now is uh, we've got two threads running, and we've got the rendering thread and the event thread. And with this event thread, when the swap chain thread, sorry, the rendering thread throws a swap chain out of date exception, that's gonna cause the event loop to be killed, because any exceptions that are thrown by uh, one one of these functions is going to cause the other one to be killed because we're racing the two. And the true is actually it's the same is actually true of concurrently as well. Any exception that's thrown is going to like kill the other thread. So what that means is that at any time during this block of code, we can get an asynchronous exception. So let's say we just got a window event. So there's a queue and we've taken an event off the queue and then we get killed. So we haven't handled that event and we can actually recover from that kill. Like we've got this retry on swap chain undate, and that's going to restart our event loop later when it recovers. So we will, like the program is continuing, but we've lost a event, which is not so good. So I think what we should do is just write a kind of thread safe version of oh, get window event. And all that will do is it's going to read the event off the queue, but install a handler in case like there's an exception. And if there is an exception, it's going to just write that event back to the queue so that we can get it next time. So pretty simple. So we've got get window event. Let's create one called with window event. So given a window, um, and then a function from maybe window events to IO. Oh, yeah, I think that's right. So blah blah blah. So we will poll for events. Then we're going to mask asynchronous exceptions or all exceptions, but in this case we're interested in the asynchronous exceptions. So we're going to do the same thing. We're going to try and read from the TQ. Then we're going to run the user's function, restoring asynchronous exceptions for the duration of its function, of their function. And then on exception, so in the case that we didn't get an event, we don't need to do anything. We're not going to write back an empty event to the queue, or we can't really. So, but if we do get an event, we're going to write, or if we did get an event and then we got an exception, we're going to write that back to the queue. Okay. Okay, that should do. Now we'll go up to our window type and we'll just reuse that function. Yeah, we can just go like this. Then we can get Haskell language server to give us the type signature. And let's just get rid of get window event because we don't really want people using that. Might as well just force them to use the safe version. So with that done, we now need to go back to our uniform example and modify this to be with window event when gosh, I don't know if you guys can hear those cars, but I have a lot of fans near my place. So in case, yep, we're going to handle the events if we get them. It's going to return if we should continue or not. We're going to put that here. Then we're going to move this. 1, 2, 3, 4. Is that the right place? Yes. Okay. So, yep, we're just getting the window event, handling it, returning whether or not we should continue, and then looping if we should. So we haven't seen that kind of case where like we've lost a window event due to an exception, but doesn't hurt to be safe. Oh, yeah, I'll have to lift IO. Cool. We're still working. And we need to fix, we just need to do the same thing in triangle and buffer as well. Let's grab this bit. So, loop, get window event with window event. Okay. Let's try and load that up. Triangle. No. Cool, that's working. And then we'll just copy this for the buffer as well, the buffer example. Ta-da! Great, that's working too. Okay, so we'll commit all this. See if we can. We'll call this exception safe window event handling. Just one more thing. Just wondering if so should this still be uninterruptible mask? Because no, we're good. We're okay actually. So the only thing I was worried about is like, remember that even within a mask, some operations are designated as interruptible, so they can be interrupted. So they're generally things that block. So if anything is an operation that might block, so might you might wait for a significant period of time. Um, they're interruptible, so like they can still get asynchronous exceptions. But in our case, if this blocks and then is interrupted, like we haven't read from the queue, so it's fine. Like we're kind of relying on STM there to uh, do the right thing in the case of a asynchronous exception. And then from there, if we receive a exception here, we're handling it. So we're all good. All right, commit that. Yeah, so I streamed this project to youtube.com at sambennett_TV. And so you can see our previous streams there, and you can follow along with the commits that we're making here at sambnt/RORT. So github.com/sambnt/RORT. And you can see our commits here. Exception safe window event handling. Cool. Okay, what's next? Okay, so something I've been wanting to do, instead of using the exceptions library, use the safe exceptions library. So that we're less likely to go ahead and swallow asynchronous exceptions. So essentially it just like distinguishes between asynchronous and synchronous exceptions and prevents you from like catching asynchronous exceptions when you shouldn't or don't want to. So like when you get an asynchronous exception, you should clean up as soon as possible, but you definitely don't want to handle that exception. You want to be like, okay, uh, fine, I got the exception, but I'm just gonna like do a little bit of work and then continue on with the program. You don't want to do that. And it's easy to make that mistake with the exceptions library, so that's why the safe exceptions library exists. So we'll just go ahead and use that. Safe exceptions, controlled exception dot safe. Okay, we're just gonna go through and change our imports to use the exception safe library. It's pretty simple. So I'm just gonna look for instances of a controlled exception and change them. That's fine. Okay. Cool. No warnings either. Let's just load one of our examples and make sure it still works. Yeah, great. So, go ahead and commit all that. Use safe exceptions library. So that wouldn't have actually fixed our problem that we were having before with the swallowing the exception in the way that we were. Yeah, safe exceptions wouldn't have fixed that problem. But just I was investigating it as part of fixing that issue, and I was like, it's probably a good idea to use this. So, what should we work on next? I do apologize. I do know that this stuff is not particularly interesting. Like, it's really important, but it's not particularly interesting. Um, really, like, it seems like what we're doing is just managing the lifetime resources and then just making sure that we're not like leaking anything when there are exceptions. Which probably brings us to our next issue, which is that in, let's say, the uniform example, we've got this thing called make frame data. It really doesn't matter what it's called or whatever, but the problem is that, so it's dependent on the swap chain. So we put it in this swap chain out of date block. Um, but so we want it to be recreated every time the swap chain is changed. So we want to destroy the old one and create a new one. Um, oh, excuse me. Oh. But at the moment, we're not doing that. So we're actually just creating a new one and not destroying the old one, which is giving us a sort of leak. So let's take, so we, in this make frame data function, we're creating a render pass. So let's go to that and we'll print, we'll change this to kind of tell us when we're creating a render pass. So we're going to create the render pass and return it just like we were doing before, but then we're also going to print um, creating and then show the render pass. Great. And then let's call it created and destroyed. Okay. And let's get rid of these. So we can just see what we want to see. Load our example. Okay, so yeah, the initial sort chain, and then we've gone and created a render pass. That's great. So when I resize the window, I expect that we'll destroy the old one and create a new one. But you can see that all that happens is that we are creating a new render pass, which is not ideal. It's only when we quit the program that we go ahead and destroy all of the render passes. So the reason that's happening is because we made a change to retry swap chain out of date. So this argument, it's like a resource context, and we decided that we were just going to let that resource context persist between these swap chain out of date exceptions. And that was because we had those frame and flight, um, the frame and flight structure, and that flame and flight thing would detect if there was an exception when using a particular frame and flight, and then if there was, destroy that old one and create a new one because the frame and flight was probably in a corrupt state if there was an exception. That's great and that solves some issues for us. But what that does is that creates a new resource in the context of that swap chain out of date block, which means that if we were to run the resource every time the swap chain went out of date, we would destroy that frame in flight. And those frame in flights are like persistent between the swap chain out of dates, like different swap chains. And so that means we will destroy the thing that we want to use in the next frame. And so that was an issue. And so we're like, well, we'll just let this, we'll let the resource context persist so that anything created in one swap chain block will still exist in the next swap chain out of date block. And we'll leave it up to the user to kind of like make sure that if they want something to not persist, if they want it to be recreated every swap chain out of date, they've got to like handle that. Um, and really, at the moment, there's actually no good way for us to do that. Like, if we were to like run resource T here, it's like a valid thing to do, but uh, the resource will only exist for like this much code because run resource T basically limits the lifetime. It like allocates it here and then destroys it at the end. So that wouldn't be very useful for us. Um, but it would recreate it on every swap chain update thing. And so, like, I guess maybe we could like run resource T like this, and then like frame datas, do block here, and then we could put like our render loop here. But then again, any like resources created here will be limited to just this block, which means that our frame and flight things will get destroyed again. So that's not good either. So yeah, we really don't have a good way to do this. Like I kind of want to use the bracket pattern. Like I want to be able to be like with make frame data, then all the arguments. Uh frame data do and then have the render loop in here. Because that way, like, I'm only limiting the frame data to this block. Like, the block can return a resource context such that, like, anything in the render loop will still, like, stay created outside of this with block. But you can't really, this is like a resource T, and you can't really do that with a resource T, which sucks. But there is a solution. So, and I think it's very interesting for us as well, like for the way that we design our rendering engine. So we have this resource T, the library, provides this uh, data structure called acquire. And acquire has some like pretty interesting properties. Like it's a lot like our resource in that it's a functor, applicative, and monad, but it also allows like monad IO, which is very interesting. And essentially what it is like you make an acquire by telling the library like how to acquire the resource and how to free the resource. It doesn't actually acquire the resource yet. You've just told it how to do it when it needs to. And so you kind of like deferring the creation. It's kind of like you tell it how to create the thing, but not when. And it'll figure that out automatically. So then once you have one of these acquires, you can do two things. You can use it like you would a normal resource. So here you've got this monad resource context. Given an acquire, you can like basically allocate something and then register its cleanup action in the monad resource context, which is great. This is how we're doing things at the moment. But it also gives you another option. You can use this with function to kind of have like this bracket sort of pattern. We're given an acquire and like a block. The resource will exist only for the duration of the block. But you can see that the context is kind of returned here. So like we can, if we're like adding to this context M uh, inside this block, that'll persist outside of the context. And we can also return a result, which is really nice. So like we can limit the lifetime of this resource to just this block, but any other resources that we create in this context will remain, which is exactly what we want. Like, yeah, this is the sort of like it's interesting thing. We've got all these resources with different lifetimes. We're trying to like interleave them and mix them together. We're like, oh, like I want these resources to only exist in this block, but then inside that same block, I also want this resource to persist, which is kind of weird, but using acquire, what we're doing is we're deferring like how we're going to allocate the resource. So no, we're deferring like, hmm, we're deferring the method of cleanup and allocation. Like you tell it how to acquire the resource and how to free the resource, but you don't tell it like uh where to limit that resource to. Like, is it going to be limited to this resource T context, or is it going to be limited to this like block? You don't you defer that decision to later, which I think is what's going to have like a big impact on our rendering engine design as well. We're going to decide to try and defer as much as possible um, till later. So we get the user to tell us like what they want in a declarative manner. So they can tell us like, how do we acquire the resources that we're going to use in the rendering pipeline? And what is the rendering pipeline going to look like? And blah, blah, blah. But we don't make the user actually create the rendering pipeline like we are at the moment. They've told us everything that we need to know. And then we go ahead and create all of that stuff in the back end with appropriate lifetimes, blah, 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 blah. Um, so yeah, I think that kind of deferring commitment is like a really good pattern in Haskell. And laziness is one of the things that helps us do that. So we're going to try and make our rendering engine thing a bit lazy. And I say that in air quotes because I'm not sure it's like it's the definition of lazy that you usually mean when you're talking about Haskell. Okay, so make frame data. What functions do we use here? So we use render pass, pipeline layout, graphics pipelines, and frame buffer. Render pass, pipeline layout, graphics pipelines, and what was the last one? Frame buffer. That's somewhere in here. Oh, that's used later on. Yes, here it is. So all I'm saying here is that, we've got this Vulkan module and it's got all of our, how to create all of our resources. And all we're going to do is instead of using our resource type, our resource type, it's great. But what it does is like, we're telling it how to allocate the resource and also to allocate it now. And all we want to do is instead tell it just how to allocate the resource, but not when to allocate the resource. So we're going to change the resource type to acquire. And then we're going to be like, make acquire. But everything else stays the same. Oh, what's going on here? Oh, oh yeah. It doesn't happen in a monad resource anymore because we're not actually having any effects here. Like we've just told it how to do this stuff, but we haven't actually told it that we're going to do this stuff right now. And so there's no longer any sort of effectful like context. So we can get rid of this. Just be like acquire frame buffer, make acquire. So yeah, it's gonna be a pretty small change, but have like pretty profound impact. The pipeline layout, yeah. And you know, the more code that we make pure, the better, really. Pure in this case meaning no effects. So that's a start. But now all of our code is going to be broken. Yeah, so instead of make frame data being, so you'll see the ripple effects up. So instead of this also being an effectful function, it's no longer an effectful function anymore. Um, yeah, so we have to change the type of make frame data. And then, yeah, we're going to have to go through and start changing some of this as well. So that should all be good. But yeah, so we no longer need to get the resource because we're in the acquire monad. And so, for example, that pipeline layout, where is it? Here, with VK pipeline layout, returns an acquire, and then we're in the acquire monad, and that pipeline layout has been extracted already. There's no need to call get. Then here, we don't have to fmap again because we're only like one monad stack deep. And same is true here. We can just turn that. Same here. No need for this sequence or this fmap. We can just do this. No need to get anymore, as we already said, and no need to sequence anymore. Oh, okay. So that should address our issues there. So maybe imports. Oh, we got acquire. Got our frame data. Okay, well, I think we need to start adjusting the examples now. Yes. So, what does this mean for us? It means that we can do what I kind of was talking about, which is we can uh, use width to limit the frame data to a particular time period. So when are we going to do that? Can probably just do it here. Let's just do it here. With make Just have to indent this all by one. And width is something from acquire. So acquiring the resource just for this block. And then where do we use the frame datas? We use them here. We don't need to get the resource anymore. And that should be good for our uniform. Let's run that example. So yes, again, what are we expecting? So we've just created the render pass for the initial swap chain, which is fine. And we expect that when we resize this window, we're going to destroy the old render pass and create a new one. So I'm not sure in which order, but doesn't matter. Yeah, okay, so we destroy the old render pass first, then we create a new one. And we've done it again, destroy the old render pass, create a new one. Now when we quit the program, we only expect to destroy one render pass because there's only one render pass that still exists. And that's true. Great. Okay. Now we need to do the same for our other examples. So when we make frame data, I'm just going to change this to width. Put this all in one line. Yes, we'll need to import width. And don't need get anymore. Run that example. Great. And then finally triangle. Width. Oops. We'll load the triangle example. And yeah, that's still working. Okay. So let's go to Vulkan and just get rid of the printing that we're doing because we don't need that anymore. Excellent. And we'll just get rid of any warnings that we have. Good just to keep on top of it. Oh, I don't want to do that. Should definitely use a formatter. Okay, no warnings. Great. Alright, let's commit this. And so fix frame data not being freed after swap chain resized. And I just have a big hunk of text for that. So won't make you watch me do all that. Cool. So we push that. Okay, so I think our next step will to be use acquire everywhere. Because I mean it only gives us power. Um, and yeah, like I said, small change, but I think will have a big impact. Certainly opening our minds to those possibilities. So it's been an hour, so I think I'll take a break and be back in like 10 minutes or so. Um, all right. Let's see if we can get a nicer color. That'll do. Then turn down 10 minutes. Great. Okay, well, I'll see everyone back here soon. Thanks for watching and um, take a break too. All right. Yeah, sorry about that. Look, looks like my screensaver uh, opened itself up and didn't want to die, so I had to do a little magic. Um, yeah, but we're back. We're back. Thanks everyone for watching. So what did we just do? We fixed some exception handling with our swap chain update issue, and then we what did we do? We used safe exception library. We did some exception safe window event handling, um, and we fixed that the issue where the frame data was not being like freed after swap chain recreation by changing the way that we acquire resources. So we're using acquire here in some of these functions, but not all of them. So I think it would make a lot of sense for us to just use it everywhere and then see what effects that has on the rendering engine. So let's do that. Excuse me. Just on and on. A little bit of adjustment there. All right, we're almost there. Okay. All right, so here we're kind of running into our first occurrence of how this changes things. So with this coffee buffer function, all we're doing is requiring a command buffer for like like period of time and then submitting it. Um, so in this case, what we can do is get rid of this run resource t and just use with from acquire to acquire the command buffers for the duration of the block. Because we're submitting and then waiting for the queue to be idle, we know that like we don't need the command buffers anymore after this point. So that should be fine. And we no longer need to use resource get because that's from our old way of resource handling. And so we've got a new way of resource handling. Looks like I've got an issue. What's going on here? I'm very confused. Oh, that'll do it. Okay, so this... Oh, looks like we're not quite done. Missed one. So for everyone just joining, where we are making a rendering engine in Haskell using Vulkan. And what we're particularly interested in doing is recreating graphics effects from like modern games. So if we have a look at frame breakdowns. So, there are these frame breakdowns, or graphic studies, where they have a look at how modern games are rendered, and then kind of take you through like the kind of render passes that are happening and the textures that are being rendered to, and you get a good idea of like, okay, conceptually, at a high level, this is how, these games are rendered. And so what we want to do is be able to express that same stuff, like that high level understanding of how these games are rendered, express that in a Haskell DSL, and then we want our rendering engine to take that high level description and then make a rendering thing out of it. So actually render the scene. So that's what we're looking at. But that's still a little bit far away. Well, that's not too far away. We'll get there soon. We just won't make anything that pretty soon. Okay, so basically everywhere here. So this is the frame in flight module, and we're acquiring resources in the frame in flight module. So we're going to have to adjust how that works. So instead of having, we're not going to use resource anymore, so we'll just get rid of that, and we'll just use the release key pattern. So we've got a queue of frame syncs which we can release. That's fine. Um, that's going to change this as well. Okay, so I'm going to read the tier queue. We're going to restore. Don't need to get resource anymore. Okay, so here's where we're allocating the resource. So rather than using just with frame sync, we're going to use allocate acquire, which is going to allocate the frame sync in the resource T context. So that means um, it'll persist when we do the swap chain out of date thing. And instead of using resource free, we'll just call release from the resource T library. And everything else should be pretty much the same. Great. But when we create the we create the frames in flight, we're gonna have to adjust that as well. So again, we'll just allocate acquire the frame sync, We'll do the same for the descriptor pool. Now that's going to give us a release key, but we're not going to use it. And then going to do the same thing, allocate acquire. And that's again going to give us a release key. And that should be good for that. Now we're not going to return when we create the frame sync, it's going to be an acquire. So again, we're deferring when we create the resource. Telling it how to create the resource, but not telling it when. So not much will have to change, just that. Because we're working in the acquire monad already, we don't need to map this over. Okay, so that should fix frame and flight. Then maybe some imports. Allocate acquire, I'm going to add that. Add release. That looks good. Cool. All right, so now we need to start working on our examples and also probably the swap chain as well. But we're getting issues with this. Well, let's load that module. Raw dots. Oh, okay. Well, that worked. Interesting. I thought I would have had to do something here. I will. But not now. Let's go. Have a look at our errors. Oh yeah, okay. Because we're not going to use this resource module anymore, let's delete it. And delete it from our Cabal file as well. Okay. Reload our library. Okay, allocator. Yep. Delete this. Now instead of this. So again, just like everything, I'm going to use acquire instead of resource. Just clean this up a little bit. Okay. And the context. Same thing, we're going to use acquire. Mm-hmm. I see. Okay. Uh, great. Should probably move all this stuff to the Vulkan module so it's all in one place. Oh, we gotta hit the surface as well. With surface. And then our implementation. With surface. Here we go. Import what we need to import. Okay, swap chain. This one will be a little bit more interesting. So we want something to free the swap chain with, so we'll need a release key. And we'll get the initial, extract that. Okay, we're not resource getting anymore. We're going to allocate the swap chain in the resource context. Just leave that as is. We're not going to free like this. We're going to use release. We'll release the initial swap chain by initializing. It's by releasing its release key. Ugh, what a tongue twister. No longer need to resource get. And here we go. Acquire the swap chain. So that's going to be make acquire. No need to resource get. It is times like these that I really wish for like some really intelligent like find and replace refactor tools. Import some things. Okay, looks like we finally reached our examples. So let's see if we can solve this buffer example. Oh yeah. Well, we can certainly find all the instances of resource get and get rid of them. So the really neat thing about acquire is that we can do arbitrary IO in the acquire monad, which just makes it a little bit easier to use. Okay, so we got rid of all the resource gets. And yeah, let's. So in this case, in the in the frame itself, we are in a resource context, so we can just allocate acquire, which will put it in the resource context. It will give us a release key, which we don't need, so we'll just get rid of that. And then everything else a little bit more complicated. We're essentially just going to have to change the way that we allocate these resources. We'll probably just try and create one big function that like initializes all of the like resources that we need at the start. But just give me a sec. Have a little think. Yeah, okay. All right, so we'll just make a little let's call it init example. And we'll take in really any of our user code. So all this stuff, everything that we're using to set up the particular example. We're going to need the context to do all that. And so yeah, you can already see like that it's inferring that this is of the acquire type, which is exactly what we want. And then like when we go like with or allocate acquire on this example, it's going to allocate everything for us and destroy it in reverse order as well. So that's great. But we do need to return something from this, and that's the render pass info. That way then the renderer knows what to do after initting this example. Get rid of all this. Then we'll go pure render pass info. And we will have to change this. We can actually have multiple render passes, so we'll just return a list. Okay. Now, the context. What should I do with that? So we can just, with EK context, oh, actually, with this. So that's gonna limit the context to existing just that block. And we'll make this a run resource T. We'll just allocate sorry, yeah, we'll just allocate the initial swap chain in that resource T, we'll keep this the same and make frame data. Okay, yes. So we want the initial data to exist basically for the lifetime of the program. So with init example context, render pass infos do. Okay, well, I think that's it. Yeah, looks good. It's still working. That's great. All right, cool. Now we just got to do that with the rest of the stuff. So the rest of the examples. So we'll copy this over, go to our triangle example. So init example, get rid of this. And we'll grab all of this user code. Blah, blah, blah. I'll grab the subpass info as well. Alright, let's take all of this. And put it in here. So we've got some bad indentation. Cool. Get rid of these. Alright. With VK context. Allocate, acquire, swap chain. Need to run resource T to make sure that we're in a resource T context. But yes, we'll allocate, acquire the initial swap chain. And then we'll need to init our example. Context. Render. Pass infos. Okay. Run the triangle example. Still works. That's good. And then we've got one more example left, which is the uniform example. So we'll call this init example. Grab the user code. Yep. Indent all this correctly. Okay, and we need to go get our render pass infos. Cool, we'll grab all that. Cool. And then we'll just return. We're going to return two things in this case, our render pass infos and our set layout, descriptor set layout. Because so the uniform example is in a bit of a state, like we haven't made it conform to the way that the other examples work, so it's a little bit different, and we will do that, but right now we'll just return the set layout. Little shortcut. So same treatment here, and I think next week we're going to look at, or next time we're going to look at resolving that. So deciding on a little bit of a better interface for these examples and making them all conform. Cool. Get rid of this. We'll need to init our example. Context. That's going to return to us the set layout and the render pass infos. Okay. Gotta load the example. Yeah, get uniform data. Oh, yeah. I indented the wrong thing. Don't want that. Yep, and we're going to get rid of all this resource get. Because we've changed the way that we're acquiring resources. Uh, well, I do like that better. I didn't like having to do resource get all the time. Looks like I've missed some. With VK command buffers. So yeah, we're just going to have to allocate the things that we want to allocate for the frame. And we'll add a little type signature here. Cool. So we'll run the uniform example, and we've still got our little spinning disk. Still can resize the window. Oh, what did I do there? Oh no. I managed to segfault it? What's going on with my screen? Oh, interesting. What have I done? So I can consistently segfault it, which is not what I want. What did I change? Does this have something to do with my swap chain? Hmm, probably not. Let me just have a look through. Oh, hang on a sec. Need to. That's a change that I made, but I'm not sure why that would cause any issues. Oh, it did cause issues. Okay, so what's going on there? Hmm, interesting. I don't know why that's an issue. Like, we've got a resource block up here, and then we didn't have one here, and that was a problem. Oh, because then I'd be like destroying this context before I destroyed any of the resources. Okay. So yeah, it's important that I destroy everything in this block first before I destroy the context. Probably doesn't make sense to like probably just want to allocate acquire the context instead of using with. Like that. And that should, automatically do the right thing for us. Just have to change the indentation. Let's give that a go. Yep, that's better. That's more like what we had before as well. Okay, well let's just do that in our other examples as well. It's a pretty minor thing. We're going to drastically change how the program looks over time, so it doesn't matter too much. But good to do it now. And then buffer with VK context. Alright, and we'll just load our examples up and make sure they still work. So triangle, can resize the window, can quit. Buffer, resize the window and quit. And finally, uniform. Yeah, resize the window and quit. All good. Okay, and finally, we'll get rid of all these warnings. So GLFW. Just going to remove our redundant imports. Window. Allocator. That looks good. Try again. Alright, no warnings. Okay, so what have we done? I think we'll just say that we use acquire everywhere. use acquire everywhere. Replace usage of resource API with data.acquire from resource T package. Push that up. Okay, so that's good. I am hoping that'll give us more options for how we make our renderer. So, use acquire everywhere. Removed the unused resource module. Yes, I think we're in a good place to have a think about what we want to do for what we want our kind of renderer to look like. So I think I'll take a quick break and then we'll get onto that. Thanks for watching, everyone. Yep. I'll see you soon. Hey, we're back. All right. So, where are we at? So we've just changed the way that we manage resources. We use acquire now from the resource T library. Um, but I think what we want to look at now is if we let's open up a little buffer and yeah. So if we have a look at this, uh, it's quite a bit we're having to do something quite simple. So we're having to acquire our resources and then compile them into a shader module. We're setting up our pipeline shader stages, creating our descriptor sets. In particular, like this is a particular bad one with like the vertices and indices. Like we've got a buffer, basically we've got to make the buffer, but we've got to make a staging buffer. Oh, hey, good to see you again, Valiant. It's been a while. Yeah, sorry, I have to apologize. My streaming schedule has been terrible. Um, I've been like have a lot of stuff going on and also trying to find a job, so I don't have a lot of rhythm in my life at the moment. So it's been difficult to like find the time for a consistent commitment. So hopefully when that sorts itself out, we should get back to a more regular streaming schedule. But it sucks to hear you're not 100%. It's tough. But it's really good to have you back. All right, so I mean, I don't know if a lot's changed since we last kind of saw things. I think the only we've what have we got? Raw examples. So yeah. So we had, we've got this example now, and we've just been looking at uh, changing the way we do resource management to make like resizing the window like actually work well and be thread safe. And also this is like multi-threaded rendering now, so like, that's good. But like not a lot has changed visually. Um, and yeah, what I want to have a look at now is in this case, like the user is having to like specify like the data, I guess, then also like allocate like staging buffers and make sure to do that before the program starts, and then put all the data in the staging buffer, then like copy the staging buffer to the device buffer, and just like lots of things like the user. Uh, is that the perspective camera moving or the actual position quaternion of the render? The camera is staying the same, but we're applying like a model matrix um, to the square to rotate it around an axis. And we are using quaternions, but like not not in any big sense. So you can have a look at this code here where we're taking two times and getting the time passed. So this would be the one would be like the start time of the renderer, and this would be the current time. So over time, we're getting like a bigger delta, and all we're doing is around the z-axis, we are um, rotating it a certain amount based on how much time has passed, and then that becomes the model matrix. I don't actually know the story about the guy who invented the quaternion. I think I've heard it before, but I don't remember. Yeah, so I mean, long story short on this is that I really don't want the user to have to worry about resource lifetimes. If we like simplified this down, what have we got? We've got some sort of like the user could literally just tell us, look, I've got a shader, shader, vertex shader, And here it is, uniform buffer dot vert dot spv. And they'll probably need to tell us some things about the shader because like we're not gonna uh, what? So apparently, yeah, he couldn't figure out the quaternion problem, and then went on a walk and he figured it out, and then he didn't have a piece of paper, so he chiseled it onto the bridge. That's crazy. It's not very often that I have a chisel. Oh, how could someone deface it? That's terrible. But like that'd be so slow. Like you know when you think, and like the nice thing about like pen and stuff is like it's kind of fast. Like you can think and like write basically as fast as you're thinking. But like a chisel, you'd have to like sit there and just be like, okay, which way I'm gonna hold the chisel, and then like bang, and then bang, and then it take forever. But yeah, the user's gonna have to tell us some things about the shader, like uh, the vertex attributes, basically, like the vertex input, because basically they're saying that like there's like some vertices coming in this location, some data coming in this location. This one's like a vec2, this one's a vec3. So we're going to need that information from the user. And we're going to need the main function name. But yeah, so essentially, and then they can tell us about their fragment shader. Do you think if I watch enough of your streams, I can put Haskell on my CV? Um, I'm not going to say yes. I mean, it's going to depend, really. I think the problem is that you'll see like one way of doing things and you like won't know why it's done that way, kind of. Like you'll just be like, you'll be able to parrot back, I guess, like what I've done. But then like what happens when you go into a new situation and it's like, oh, we need you to understand this new thing and then we'll apply your Haskell knowledge to this new thing. That's going to be a lot harder. But Haskell's fun, so you should just do some of your own stuff. Okay, so what other information do we have? We have like a bunch of information about our descriptor sets. And then like I have a vertex buffer and then like there's data in it. So in this case, it's like literally just some floats. And I have an index buffer and yet some numbers. So I'm just writing down everything that the user actually needs to tell us. And the rest, we can just figure it ourselves. Like, I'm thinking like we've got this new acquire type. So if the user gives us uh, an acquire type that's like read this file and it's like an obj file, or maybe we call it open file, and then close file. So if the user gives us this, and let's say they call it vertex data, then they can just say to us, look, I want this vertex buffer, here's the vertex data, and maybe we can give them back like a handle, like say v. Now we haven't actually allocated like that vertex buffer. I mean, from the user's perspective, like they're not going to really know, but like we haven't allocated that buffer, and then like the same for the index buffer. But we do know how to. and we do know how to put the data in there because the users told us how to, but they haven't told us like when they want it, which I think is the problem here, is like not only are they telling us what data they want to fill the vertex buffer with, they're also telling us when they want that to happen. Like they're having to say, I want it to happen at the start of the program, which like is fine. It's not a problem, but it's not really what we want. What we want to be able to do is like, you tell us what to do and we'll decide when to do. If I'm sure it'd be fine. If they really wanted the data, they'd use the function you haven't written yet to get it. Yeah, exactly. Yeah. So, uh, yeah, like the reason is we want to keep the interface simple, and then in the back end, we want to be like doing all the complicated stuff. Like the user doesn't really care that we have to upload to a staging buffer first and then upload to the like device buffer. Like really don't care, also don't want to care, and makes it complicated. And it also kind of like limits us. So like the more control that we give to the user, the less control we can have, um, which is starting to become frustrating because it's like I want to do things like allocate a massive buffer, like just one massive buffer, and then put all the user's data in there. But when the user has to allocate that buffer on our behalf and then give it to us, it is this weird kind of like control issue, like where they've got too much control, we don't have enough. So I think we can change that. And we're going to use that acquire type. So the user tells us how to acquire the data, but not when. And then we decide when we're going to do that. And then like with that data, we can do all the complicated stuff. So I kind of want this whole, 450 line program to be something like closer to this. Let's try and figure out what that'll look like. So they might be like shader, vertex, uniform buffer, and then they're like data. Yeah. It's not like we're trying to take control away from the user like on purpose, like to like power play or anything. We're just what we're trying to do is like this like Vulkan's very complicated and like resource lifetimes are really important and making sure that the resources that they create stay around for the frame which is being rendered. But it's kind of like asynchronous, like the frame could be rendered over here. We don't actually know when it'll finish. We have to use all these synchronization primitives to figure that out. Like we don't, if we give the user control over creating those resources, then they have to be worried about keeping them alive. Whereas if we have control, then we can be worried about that, and it's a lot easier for us. Now, obviously, I'm probably going to be the only ever user of this, so maybe it doesn't make sense, but this is an important way, I think, to like create good programs, is to think about the difference between the user and you. Like, what does the user want? What do you want? In like 4 months' time, I'm going to want a very simple interface for declaring, describing high-level render passes. That's what I'm going to want. And I don't want to be worried. I'm like going to forget about all of the intricacies of Vulkan. I want to encode that in code so that I can forget about it later, because that's going to happen. So, what else do we need to describe? We need to describe like our subpasses. So, what does that look like? Hmm. It's kind of hard thinking on stream. So, I mean, yeah, it'd be something like subpass, and like a subpass is made up of shader stages. So we've got our two shaders. I mean, it's got a list of descriptor set layouts. Descriptors. I don't know. I'll just put descriptors. So these are like our bindings. Let's call it bindings. And then we've got like our vertex input. And that's kind of it. I mean, here we do have this draw, but this is kind of dynamic. Not sure we need to like put that here right now. Uh, the less you have to think about the back end while working on an actual application, the better. With RayX, the Elixir thing, I make everything like a helper function. So init window will do a bunch of GL stuff. Yeah, yeah, exactly. Yeah, yeah, that's great. That's what we want. So, just the reason I'm a little bit hesitant to put like this stuff here is like, this subpass, like this kind of shader, like collection of shaders rendering like a image basically. Like, uh, a lot of it is fixed. Like all of this stuff is fixed. You know, we have to use the same shader. We have to use the same bindings. The vertex input can't change because like the shader is basically like a program and it's kind of frozen in time at this point. But what can change is like what we draw with that subpass. So like, you know, I could draw a triangle one time and then the next time draw a sphere. And there's no problem there. Like that can dynamically change. And like I can bind you know, the ogre vertex buffer one time and then bind the dragon buffer vertex buffer next time. So I'm going to call this like dynamic data and then maybe deal with that later. So like what, subpass one and then render pass. Hmm, yeah. Um, in this case, render pass is just made up of subpass at the moment. So we can just keep it simple. Cool. Then we assume that all this stuff is handled for us. All this crap. So like, let's imagine that we're in a render loop. So all this stuff has been declared beforehand. Maybe it hasn't been allocated, but it doesn't matter. And then we're going to do our draws. So like, how do we do that? We'll go like for each like object. In this case, we've got our little spinning disk, little spinning square, and uh, we're feeding in time basically, like delta time into the loop, and we're being like, the new rotation of the square is like delta time plus some maths. And then what are we doing? We're allocating uh, a unit, like allocating like a uniform buffer and giving it like a particular size. And then we're, let's say we're, so given the rotation, we're making some matrix, we're allocating um, a uniform buffer the size of the matrix, and then getting back like a pointer, and then we're uh, poking poking the matrix to the pointer. Yes, yes, I could use keyboard events to like change the speed and stuff. And we'll get there. Like, I did a little example. just a proof of concept of using like functional reactive programming to to like uh, make like a bouncing ball that we rendered. Um, I've kind of left that on a draft branch at the moment, but yeah, that's like a it was a really cool like concept where um, we describe like a bouncing ball as a function of time, and then yeah, we kind of just like hook that into the renderer and get the renderer to render that, which is like really cool. And I did think about streaming that and like showing it on the stream, but I just you have to change the renderer a little bit to work in a step-based fashion where instead of having like full control over the loop, we're just like tell the render one frame, render one frame, render one frame. So I had to change the renderer to do that, and it just got a little bit complicated. So I didn't want to like do all that on stream and stuff. Um, but we'll get there because like essentially what I want to do is this first, make it nice first, and then we can like change it to a step-based renderer where we just render one frame, one frame, one frame, and then we can like hook it into FRP or functional reactive programming, and like we can make a game in functional reactive programming and then hopefully render it. That would be like sick. So I'm excited for the next, couple of months. But yes, we have to make the interface simple first because otherwise things get a little bit out of hand. So this is what we're doing at the moment. We're like making a matrix for each object, like its model matrix, and we're like poking it into a pointer, and that works fine. Just wondering if that'll have to change. What else is happening here? We're allocating some command buffers. We can pretend that that's being done for us. All of this crap. So here we go. Hmm. Yeah, yeah. Hmm. So this is just where all the dynamic data is. So like I said that in the subpass, it's kind of like dynamic elements, like is it a dragon, is it an ogre, that sort of thing. Um, and this is where that rubber is hitting the road. Because it seems like we basically want to kind of like begin a subpass. So like begin subpass one, or even we have to begin the render pass, then begin subpass, and then we have to like bind vertex buffer v, and like bind index buffer I, and like bind uniform buffer that maybe we get from here. U, we'll just call it U. This is all very speculative. And then draw index probably, and then whatever else. Will that work? So like at the moment we're getting the user to like give us basically every draw call like upfront. So like they give us the render passes, they give us each subpass within that render pass, and each subpass has a draw call. And that means that for a given subpass, we can't like have multiple draw calls. So we can't draw like one object and then draw another object or whatever. That just doesn't work at the moment. And that's why I think it's important to separate this dynamic part from this static part. And so we've done the static part up here. But the thing is that we then need to, when we're going through and rendering the objects, we need to, yeah, we need to make sure that, um, make sure that we're doing this right. Do I think that this block, or do you think this would block having multiple objects in the scene? Yes. Yeah. Like not hugely. I mean, I can easily change this to just be like a list of draw calls, you know? But even then, like, then you still have to decide on the draw calls up front, which I just think is a little bit weird. And I think actually that's what's actually more like what's happening is like we're not going to make a render pass for each object. It's like we're going to start the render pass like mm, in this case we only have one render pass, so let's just say one render pass. And then because it's kind of like we're making something so that we can make like a high level render pass description. So we already know about the render passes, like that's something we are already like aware of. And so we're like, okay, we want one render pass to render all of the opaque objects, and then another render pass to render all of the transparent objects. So I think it's more likely that we'll be like, okay, begin opaque render pass, and then we'll, for each opaque object, be like, object dot v, object dot I. Yeah, yeah, yeah. I just like, I'm not very, I've made rendering engines before, but like, it was very like specific purpose. It wasn't very general. And so, we got away with a lot of crap. And so I've looked at general purpose rendering engines. Um, like, this is one that I've been referring to a lot too, because I liked this talk. Um, and yeah, this is what they kind of like have. They create, uh, their vertex buffers, their textures, their shaders. They're like these big descriptions that are then created and get handled back. Um, I mean, this is all in C++, of course, but then their draw loop kind of looks like, for each object. Um, oh yeah, okay. So I guess their pass would be up here, like further up above this code that we can see. Yes, absolutely. And we will handle all of that. Um, yeah, it's like we'll get when the user describes their render pass and stuff, like it'll describe the dependencies between the subpasses. Um, so like it should be all good. We just got to think like we're thinking sort of high level here of just like do this render pass, do the subpass, but like Vulkan will kind of like might execute subpasses like concurrently if it can, based on what the users told us about, you know, the dependencies between the subpasses. So yeah, but yeah, it's a good thought. It's a good thought. So yeah, I guess in that case, they've got like passes. They're setting the binds for like a particular pass. So like, I guess like in this case, that would be like up here. They'd be like, okay, bind uniform buffer material dot uniform, and then for each opaque object. So there might be material properties, and then there might be like model properties, like the model matrix. Hmm. That feels alright. begin render pass, begin sub pass. Just a little bit hesitant because I'm doing it differently here. But that's okay. I think that's just a normal human thing. Yeah, so basically when the user calls begin render pass, we will begin a render pass. Yeah, absolutely. Yeah, texture maps and height and normal maps definitely be a big part of this. So yeah, they should probably tell us about the clear values, the render pass, and like extend. Oh, emission map. Yeah, so like an emission map's like lighting, basically. Makes stuff look glowy. Is that true? Hmm. Yeah, I do really like glowy things. It's just very cool. Yeah, yeah, I can't wait. Like the idea of like, like even just something simple like I make an example where it's like you click on a surface and like it makes a sound, like as if something hit that surface. Like that would be so cool. Just have like different surfaces that make different sounds. Well, that's what we should do. When we get something that like when we get like a decent sort of rendering structure, maybe not perfect, but just decent, we should try and like do something with emissive maps just to get some cool glowy effects. So I think the thing I'm struggling with here as I think about this is just that up the top here, we've got a kind of declarative um, interface where they're telling us what they want, but they're not telling us when they want it. So yeah, they're kind of handing that responsibility over to us. But then in the render loop, the timing is important. Like they're telling us what they want to bind and when. Like they're saying begin render pass one now, and then like set the viewport, and this is up for like this, now, and then bind this uniform buffer now, and then for each object. So like the order matters. Like um, these are sort of deferred, and then these are sort of instant. And that's what I'm just struggling with a little bit in my head because I'm like, it feels wrong because like surely they should just be both more declarative or something. But I think it's fine that this is more instant, and I think it matches what people would think about anyway. Because I guess how I was trying to do it before was instead of doing like begin this, I was going like, okay, this is render pass one, and render pass one, the viewport is this, and the scissor is this, and the subpasses are, like subpass one, where the draw calls are this. This is like, this is more deferred or like declarative, where they're telling us what they want, but then they're not sort of telling us when. Um, so yeah, I mean, maybe we can find a middle ground at some point. But I think we kind of just need this right now because this declarative one isn't working for us. Oh yeah, like load, draw, update. Yeah, yeah, yeah. No, that's a good, yeah, good way to think about it because that's essentially like all of Vulkan is just this resource management of like, yeah, we've got this load phase where we're like loading things that are persistent, but then we also have things like uniform buffers that maybe aren't persistent. You know, they're persistent for one frame. We've got these different things with different resource lifetimes. Like this one's present for the whole program. This one's present just for these frames. Um, or yeah, like you've got your update and then you've got your late update where you've got like this two-stage update. It's, you're right. It's, that's a good way to think about it because like otherwise things can get complicated. You're like, there's so many different lifetimes. Okay. Yeah. Yeah. All right. Well, that might be good enough. We'll just like we'll allocate a command buffer. So like they might be like, I don't know, with render frame or something. And then we'll allocate a command buffer and we'll make sure to submit it and stuff. And then they'll say like begin render pass one and we'll admit a graphics API call, which is begin render pass. And then they'll say set viewport and then we'll say command set viewport. So the way that like this one's interesting. The way that they do this is like when you say like set shader, it doesn't actually set, it doesn't emit a graphics API call immediately. What it does is like it uh, sets like a particular bit in a structure, and then later on something goes through all of that and will what's the word for it? Will then emit an API call later. Yeah. So I think that's ultimately what we'll go for is like again deferring where the user's telling us what they want, but then we'll not execute it immediately. We'll execute it a little bit later on. So we have like a little bit of control um, over things. Like, for example, uh, a problem we might run into here is, let's say I'm going to annotate each of these lines with like a particular API call. So like, I'll just put a little tilde and I'll be like, with render frame, okay, we're gonna allocate, so like Vulkan allocate command buffer. So we've got one command buffer. The problem is that like the user might be like, oh, I'm really intelligent, and what I'm gonna do is like multi-thread this. So I've got like one thread's gonna do like all the like half the opaque objects. I don't know, 0 to 50, and then another thread's going to do all of the opaque objects from like 51 to the end of the list. And that might seem really smart. And then they're going to make their draw calls and stuff from multiple threads. But the problem is that you can't record, multiple threads can't record to the same command buffer. In fact, like multiple threads can't record to command buffers allocated from the same pool. So um, what we've essentially done is like prevented the user from multi-threading their draw calls. But what we can do instead is instead of actually admitting like an API call when the user, does this, like BK begin render pass, what is it? VK command begin render pass. That's the actual API call. Rather than when they actually call that, we emit it straight away. What we can do is like basically create a data structure. Ah, see, I think that's the problem. Sorry, okay, finish my sentence. We'll create a data structure that we accumulate, and then we can go through later, and then we can split those up into different threads, like on behalf of the user. Um, so that way we can kind of like get what the user wants, but they don't have to like worry about that. Yeah, and we get a little bit more flexibility about in what order. Like we can reorder the draw calls. Like if the user's chosen an inefficient order of draw calls, we can reorder them. Um, so yeah, and what I was gonna say is like the problem. Let's. I said that there's dynamic data here, which is true. The problem of this data structure. Hmm, what am I trying to say? I'm trying to say we can have a declarative type here. So the user, instead of saying like all of this, they can say instead, and this isn't what they're going to want, but like we'll make a better interface, but they can say draw render pass equals render pass one. And then it's probably going to be like this. Viewport equals this, and scissor equals this. So they can declare, so in declarative fashion, rather than imperative fashion, they can declare what they want. They can put their draws in here, like draw calls equal list of draw calls or whatever. And then we can take that information and like multi-thread it and bind the right vertex buffers and all of that stuff. So that's probably where we'll arrive. Sorry, I'm probably not explaining it very well, and I'm kind of using terms that are very like Haskell specific, like declarative versus imperative. So maybe I should describe that again. Like declarative is like the user tells us what they want, but they don't tell us like when they want it, or like what or like the exact execution time, all that kind of stuff. That's kind of left up to us as the rendering engine developers. And then imperative is a little bit different, where imperative is like, oh well, like when I call begin render pass, like I want you to emit VK begin render pass to Vulkan at that exact point in time, and that reduces a lot of the flexibility we have as rendering engine developers. Like on the backend side, the client has like more control, but then the backend has a lot less control. And what the assumption we're kind of making here is like, well, the client actually is going to be me in 4 months when I forget all of the intricacies of Vulkan. And so I don't want me to have control. I want the backend person to have control. So when I say declarative versus imperative, that's what I mean. So I think that's what we'll do here. I think the only imperative part will probably, oh, well, we don't even need that to be imperative. So the user will probably create a structure that looks something like this. And like they might be like uniform buffers. And they'll give us like the data, like a matrix. And they'll be doing this for each object. So let's just comment out this for a sec. And there's nothing wrong with this one down here. In fact, we can actually make this declarative, and we like maybe we'll get there. But for now, we'll stick with this because it's a little bit simpler for me to implement. So it'll look like, okay, for each opaque object, do this. Let draw equal, and then like record draw or something. And we'll get all the same information we're getting here. It's just in a single data structure. And yeah, that gives the user no illusion that they have any control about when this will be executed. And it gives us all the control, which is great, I think. So yeah, I think the thing I've realized here is that yes, there's static data and then there's dynamic data, and we've just got to create two separate data structures, one for the static and one for the dynamic. And so all the static will be declared up front, and then in the draw loop, we've got a separate data structure that we use to record all the dynamic data. So I apologize if I lost anyone there because I'm like thinking on stream, which is like not my favorite place to think. It's really helpful having you guys to like listen and me to like rubber duck with that. But yeah, I apologize. I know it's like maybe not the most fun to hear. Um, so yeah, but point is all of this code, which is like 450 lines of code to render a square, could just like, if you think about it conceptually, like what are we doing? We're declaring the vertex shader from a file, like we're loading a fragment shader from a file, we're loading some buffers, we're describing a subpass, and really there's no more information than that. Like this is this is a simplification, but this is basically all the information that we need to render that square that's spinning around. But this is only like, say like 40 lines of code. This is like 450. Um, there needs to be a translation step like between this in the back end that I think we'll start on next time. We'll take this declaration and do all the Vulkan stuff we need to do. Like for example, the user will declare a vertex buffer, and then they'll give us like how to make the data that we'll fill it with. But we won't actually make the vertex buffer at that point. And they'll ask for an index buffer, and we won't actually make the index buffer at that point. And like later on, at some point before we start rendering, what we'll do is then we'll create a massive buffer that can hold all of the vertex buffers and all of the index buffers that they've declared. And then we'll just like shove all of the data in there for like allocation efficiency, because like in Vulkan, you can only allocate a certain number of times. So you want to allocate as little as possible, or the least number of times possible. So yeah, and that's an example of how taking a declarative approach gives us more control. The user thinks something's happening straight away, but it's not. It's happening like later. And then at that later point in time, we have more information than we did at the instance the user asked for that vertex buffer. Because like in this line, all we know is that there's one vertex buffer. But on this line, we know that there's a vertex buffer and an index buffer. So we have more information. So this is all about deferring commitment until the last possible moment when we have the most amount of information possible. And like right before we need that information, then we can go ahead and make our big data, vertex buffer. And the same will be true of the shaders and other resources that we create, like textures. So that's a massive rant. If you have any questions, chuck them in. Happy to answer them. But I think we'll finish on the 3 hour mark, and we'll come back to this exciting part. Like for me, this is really exciting. This exciting part next time. And hopefully we can kind of take our examples and reduce them down to a really small footprint, and then we can start building out a lot more examples. You have to understand, I don't talk much in real life, so this is like a lot of talking for me. But if there are no questions, it's great to have everyone on the stream, and I really appreciate it. Yeah, go ahead and follow if you want to keep up to date with when I stream. And yeah, I probably won't have a streaming schedule for the next week or two, but after that, we'll get back onto the usual schedule. So thanks so much. Sweet. Thanks, Valian. I really appreciate you coming on the stream. Like, it's really great having someone to chat to, um, someone participating. So thanks so much. I really hope you get better soon. Be great. All right. Thanks, everyone. Have a good day, and thanks for joining the stream. And go, play around with some Haskell. And one last thing is that all of our previous streams will be uploaded to YouTube at SamBNT_TV. So that's at SamBNT_TV. You can see that here. And then this code is uploaded to GitHub at SamBNT/RORT. So you can follow along. So yeah, thanks so much. Have a good day.